Hello, everybody. Good morning, good afternoon, good evening, wherever you are in the world. Thanks for tuning in, and I hope you're having a brilliant day. Welcome to the Polyhedra Show. I'm Anthony, and today we are diving into what is one of the most fascinating cryptographic protocols powering the next generation of verifiable computation. So we're going to be exploring how the GKR protocol is becoming the foundation for both zkVM, zero-knowledge virtual machines, and zkML, zero-knowledge machine learning implementations. And I'm super excited for this one because I'm joined by two of the leading and most brilliant minds in this space. First, I'm super excited to welcome Hai Chen, the co-founder of Scroll, who's been pioneering work on Sino, a cutting-edge zkVM platform. And we're also joined by, of course, Dr. Zhenfei Zhang, our chief cryptographer at Polyhedra, who's leading our efforts in making AI verifiable. So welcome to you both. Thank you so much for joining us today.
Thanks for having us.
Yeah,
Thanks for having me.
Yeah, thank you for the introduction.
Great to have you here, guys, and great to meet you, Hai Chen. Really appreciate you being here. So just to get started, Hai Chen, can you give us a background on your journey so far and the work that you guys are doing at Scroll?
Mm-hmm. Yeah, so hello everyone, I'm Hai Chen, I'm the co-founder of Scroll. Scroll is a zk-ROP layer 2 to scale the Ethereum. So our mission is to using the zero knowledge and the cryptography to seamlessly to scale up the Ethereum to achieving lower transaction cost and a higher throughput without sacrificing any security. So so what we do is we're using the zero knowledge technology, especially more on the verifiable computation side of the zk technology to verify all of the transactions happens on the layer 2 so that we can prove that all the transaction has been processed correctly and truthfully based on the protocol definition specs, and then so that the transaction can be settled eventually on the Ethereum. So we've been building Scroll for almost 4 years. And last year we've launched our mainnet. Mainnet we've been launching I think for 2 years, almost and then very recently we also did a big upgrade that we initially built the zkEVM, that's using the Halo 2 and the Snark and Plonk to build the first zkEVM. And now we are recently upgrading and then building the next generation zkVM called Sino. Yeah, that's a very short brief introduction.
Awesome. Yeah, thank you for the introduction and to dive into a little bit high level of what you guys have done and are doing. And I'm sure we're going to dive in deeper to that. So I'd love to start with a little bit of context for our audience today. When we're talking about verifiable computation, many people think of this as a theoretical concept still, right? But both of your teams are building real world applications of this technology. So Hai Chen, could you briefly explain what we mean by verifiable computation, why it matters, particularly from Scroll's perspective?
Mm-hmm. Yeah, totally. So I think the Scroll, as I briefly touched, as a Scroll is a layer 2 for the Ethereum. So what layer 2 means to users is that user need to move your assets on Ethereum to a layer 2 blockchain. And so how user can be sure that your asset has been processed correctly? So because currently most of layer 2s are running centralized in a centralized way. So that means the centralized operator may behave malicious. So what we do to guarantee the user access, the safety and security of the user assets is that we will prove all of the transaction that being touching users assets and then changing the balance sheet. So those things are being verified by a very particularly designed the zkVM to prove that all of the transaction is processed correctly, and then your balances are very safe on the layer 2. That's like what the verifiable computation is like. All of the transactions are basically a small computation on top of the ledger, like that holds like all of users' assets, and then we are making like changes to those assets.
Brilliant, brilliant. Thank you, man, and thank you for that explanation. Zhenfei, man, can you add to that? You know, from an AI verification angle, like how does verifiable computation relate to what we're building here at Polyhedra?
Right. So if you view like all the transactions on Ethereum as like virtual machine executions, then the verifiability for Scroll or for the Signal would be like you have a set of opcode executed, and then you have a proof that this execution is correct. Similar things happens in our zk PyTorch. So when you have a set of executions that execute the say PyTorch logic or the machine learning inference, and then we will just generate a proof showing that okay, this inference is generated correctly. And this, I mean, in theory, would be the same as a zkVM or the zkVM, except that the computation that you carry out would be different. Whereas in the zkVM, you carry out the computation as transactions, where here we do the inference, the matrix multiplication, the different kernels in the AI models.
Awesome. Both obviously so complementary and addressing like such important things. So it's really cool to get to like get to talk to you guys about this, and it's super fascinating. Hi Chen. So I understand that Scroll has developed Sino as a next generation zkVM platform. Could you tell us about how it utilizes the GKR proving system?
Yeah, sure. Yeah. So Sino is like pioneering a new approach for the zkVM design. I think the most significant changes that we are integrating the multivariate proof systems. So where like all of the other existing proving system are using like univariate proof system, like most of the like I cannot say like all of them because there's some like the other like the approaches there. But yeah, I think like our goal for the Sino is trying to achieve the real-time proving and also to offer the cheapest proving cost for running the zkVM with the lowest proving overhead. So what like the core center of this multivariate zk proof system is like the sum check and GKR protocols. So these like are some of the very elegant like zero knowledge technology that can achieve like close to linear proving time with respect to the input size. So which dramatically reducing the overhead compared to other things like it's quasi it's like a logarithmic proving overhead with regard to the input size. So that we like design like the purposefully like for the circuit, including the front end and back end to adopt this GKR backend to write the circuit. And then we also have some of the design, like redesign of the zkVM circuit architecture that like we adopts like a no CPU chip type of design, which can reduce the circuit size and cross-chip communication.
Very fascinating, very fascinating. I actually had a note here because I understand that GK, and I want you guys to fact check me on this. It's the Goldwasser Kallai Rothblum. Did I get that?
Right.
Yes. All right. The GKR protocol. It's been central to Sino's design. Yeah. Very cool. Can you tell us about the role that this plays in next generation, zero knowledge virtual machine?
Mm-hmm. Yeah. So I think like GKR previously, it's like design. It's a layered circuit design, which like in each layer you're using the sum check protocol to solve like to do the verification. But I think like people used to treat like GKR to work for those data parallel algorithms. I think like a machine learning or other like the type of well formulated program. So people like didn't think like we can use the GKR to design a zkVM. But like what we actually design so how like the GKR, we found out like how to use the GKR to build a zkVM is that we realized that in your VM instruction, like the execution trace, you have lots of like the repetitive same instruction, for example, the add opcode, like the multiply opcode, and also some register movement. So those like opcode like being repetitive, like executed multiple times, and then so we design like an innovative way that we can reorder those execution trace, and so that we can pack all of the same instruction executions into a same single circuit inside GKR, which will be well suited for those GKR type of the circuit. We can process all of the same opcode in the same circuit like in parallel. That's like some of the core design like in the CNO for doing that. And then like we use like other like a lookup GKR. So there's some new protocols allow those. We can insert that. We can assert that the transition cross like before and after each instruction are done like correctly, so that you can pass in the states across like different instructions, even after you reordering the execution trace.
Wow. Okay. Brilliant. Fascinating. Fascinating, man. I want to talk. Let's talk Ethereum Beam Chain. Obviously, betting big on zkVMs. How is Zeno positioned amongst all the candidates? Is the GKR protocol the secret weapon that you have here?
Mm-hmm. Yes. Yeah. So far, like I think currently, like Zeno is still a kind of early phase design, like the protocols. We've been building that. Like we currently like the status, like we have all of the RISC-V RISC-V instruction sets has been supported. But we're like now adding more precompiles like CATCHAC, ECDSA, like those elliptic curve operations there, like into the Zeno. So it's still like a halfway through that. But we do believe like the Zeno or like this kind of GKR and multivariate zk-proof system zkVM design will be the end game for the zkVM, because it has the most like the advanced and then the most efficient zk designs. So we do think like the Zeno will be positioned like very well along the Ethereum Beam chain, and then also integrating like zkVM into the Ethereum protocol. I think Zeno is very like a strong candidate for that, because like the Zeno can deliver the fast, efficient like the way like to implement the zkVMs, and also the Zeno is designed very like the modularized, and it's very simple. So we do believe like the Zeno can be also very suitable for like doing the formal verification, proving the zk circuit is correctly like done like inside the Zeno. Yeah, and then I think like the GKR, we do believe like it will be the future of the zkVMs.
Brilliant. Love it. Thanks for the insights there, man. I really appreciate it. And on that same vein of GKR, it seems to be the common thread through the projects, right? Through both your projects. Zhenfei, I know you briefly worked with Scroll. Could you and on Zeno, I believe. So could you share your perspective on GKR and why it's so important?
Right. Yeah. So I mean, let's go back to your previous question, where we're talking about Ethereum Beam chain, and the Zeno is really good for the Beam chain. So I mean, I believe that when we try to build something, right, we build a new proof system. We do not look at its existing state. We look at it when it's getting deployed. So for Beam chain, it's obviously at least 3 to 5 years away from deployment, and we are actually building a protocol that is targeting that time frame, not right now. So for that, I think we really need a new generation of provers. If we are still working on this generation of prover, then say the Plunkish or even last generation prover like Grok 16, then we are not making progress. We will be obsoleted when the next generation comes. So what I have in mind, or what I believe was, why the zkR is so important is like it's really the next generation. So if you compare the prover complexity that Titan just mentioned, it's linear, whereas the Plonkish and Gross16 are always quasi-linear. So from the theoretical point of view, it's going to be better. We will just need to spend a lot of effort to make it there, and compare with the effort that you want to spend on the this generation. Like it's the effort you spend on this generation prover will almost get wasted if you believe that they are the next generation in zkR. So that's my philosophy. Like you should always work on the on the next generation of the stuff.
Really interesting, man. I love that perspective. You know, work on the next generation. Do you think that time frame for Beam is still accurate based on everything that you guys are working on?
I have no idea. It's way beyond our capacity. Yeah.
Yeah. I see leaps and bounds ahead, man. Based on talking to you guys, it's super cool. For our audience who might not be familiar with the technical details, could you highlight the major differences between zkR and other protocols you mentioned, like Plonk? Maybe Haichen?
Yeah. Oh, okay.
Yeah, I can explain first, and then Zhengfei, you can add more. I think you're more expert in this. So I think zkR is designed as a layered arithmetic circuits where gates are organized into layers, and then each layer will only connect to the previous ones. And then underlying the zkR, each layer, it does use the sound check to check the layer are connected correctly. Whereas I think compare the Plonk is more I think that the major difference is zkR is still a multivariate circuit, the proving systems, where the Plonk or Stark, they're all still a single variate circuit. So what does it mean? For example, you think there's a function. So what the Plonk or Stark does is that it's just fx equal to y. That's your polynomial. Whereas in the zkR, you have the fx1, x2 up to xn equals y. So it's multivariate inside your polynomials. That's the one major difference. And then also as a proving time, it'll be different where the zkR is near linear proving overhead, where with regard to the circuit size, where a Plonk or Stark, because they need FFT, those kind of things, they often it's quasi-linear and has a higher constant factors. And also zkR does not require a trusted setup. Stark also doesn't require that, but the Plonk will require a universal trust setup. Although it's reusable, but still has some trusted setups there. Yeah, so this is something the highlight between the difference between zkR and other proving systems. But Zhengfei, if you have anything you can add to that.
Yeah, I think Haichen has summarized this very well. I will just mention why it's so good for the neural networks that we are doing, right? So for zkR, there's actually a dedicated prover that is used for the matrix multiplication. So if you are familiar with the AI space, you know that the majority of the computation was done for this linear transform. So it's basically vector matrix multiplications that you need to do during the inference. And this takes the majority of the computation in circuit. And for zkR, you can do it with a single gate or single layer. You will be able to prove that vector matrix multiplication is correct. Whereas if you use a Plonkish Plonk or the Gross16 kind of solution, you are looking at a squared or cubic size of the circuit. So that's a huge difference. So that's why it is so good for that is why zkR is so good for neural networks or for the MATMOuse. And the other advantage that I think Haden just briefly mentioned about the data parallelism. That is, say, if you are computing, say, two matrix multiplication, if you are trying to prove two matrix multiplications of the same size or same dimension, then you kind of can aggregate those two MATMOuse into a larger proof. So that's a data parallelism. So the same circuit, but with different data, then you will be able to merge them. So combine those two advantages, you get a massive save on the proving time for the GKR protocols.
Awesome. Thank you so much for sharing, gentlemen. I think I followed on about 20% of that, which is a huge win for me, Zhenfei. I think I've been talking to you so much. I'm actually like, you're teaching me a lot, man. But you guys obviously it reminds me of being, at university, when you're listening to a professor and you're like, wow, this is it. And then it's like, I've got a lot of work to do to catch up to even understand this. But I know I'm looking at our community comments here, and I can see that there's some brilliant minds in our community as well that are really appreciating it. And yeah, a lot of love for you guys and what you're sharing. So thank you so much on behalf of the community as well. But let's move on. So Haichen, I understand. So Zeno represents, obviously an advancement over previous zkVM kind of implementations. Could you share some of the innovations that make it so next generation?
Yeah. So I said so previously I mentioned a few points. One is by how to design using the GKR to design the whole circuit for the zkVM, which is already some new innovation there. And then also our circuit design, because of using the GKR, is slightly different. We are getting the one chip per instructions inside your inside the zkVM. So for example, add, we have one add chips, and then for multiply, we have multiply chip. We don't need to has a centralized a core CPU to do the dispatching, do the decoding itself. We can directly the kind of dispatch all of the instructions where when a program execute, we can dispatch all of this without a centralized circuit to help you to do the coordinations to do that. It's we call a no CPU chip zkVM architecture. So I think this is something innovation, and also it's derived from by using the GKI as the center of our proving systems. And then I think we have some the upcoming optimization also proposed in the Zeno original paper, is that we have this kind of auto fusion optimization that we can fuse a few the repeated structures inside a program, the loop bodies, into a single fused circuit. Now this can reduce the overhead for being you need to communicate across different chips, different instructions. It can reduce a lot of the inter-chip communication inside your zkVM. And it's very similar to how FPGA being can be more efficient than a general purpose CPU. Is that a FPGA, you have a specialized program, then you just fuse inside your FPGA chip, so it can be 10 times more efficient than the CPU. So that's kind of another innovation to inside the Zeno. And then I think I think similar to other this, the GKR, we can design very efficient precompiled circuits, which I think one of the beauty for GKR is can hiding a lot of intermediate computation results from being into the data commitment, because the data commitment inside ZK whole ZK process, it occupies a large chunk of the time of your proving time. But the GKS, because in the layer circuit, if in the second, only the first layer, the data need to be put into your polynomial commitment. All of the intermediate layer, a layer above that, you can hide this from the data commitment, which says you can reduce the overall proving overhead. Yeah, that's pretty much it for the kind of innovation inside the Zeno.
Thank you, man. Thank you for the insights. If there's two things that I love, it's innovation and optimization, and obviously you're hitting both. They're very very great. I love it. Obviously both projects pushing GKR in very complementary ways. Zhenfei, can you talk to how does ZK PyTorch differ from and complement Zeno?
Right. I guess so far we've all talked about the difference, like the Seno is proving a EVM, proving a virtual machine execution, while zkPyTorch is proving a machine learning inference. So so for this question, I guess I will just focus on how it complement each other. So I mean, from our point of view, like when you prove a machine learning, right? You can use zkPyTorch, but that only prove the zkPyTorch only prove the inference itself. So say that means like if I have an input, I have a model, and I have output, I prove to you that the input going through the model will generate output. So that's all what zkPyTorch does. But in real application, what you do is more than that. You need to say, for instance, load the model from the disk. You need to say, for instance, show your output and sign it, so that authorize it, and then send to a third party. All those things. If you view them as program executions, right? And they are. You can actually prove them through the zkVM. So, for instance, if we have a risk, I mean, if you just compile all these additional logics into RISC-V opcode, then you probably will be able to prove those logics with Seno. So what I'm trying to say is like, okay, from the user point of view, you have end-to-end process, and the code part will be the code part will be the machine learning, and it's proven by the zkPyTorch, and there are quite a long tail of auxiliary executions where you prove where you do all these auxiliary things that I just mentioned. Those can be done with Seno. So combine those two, you kind of get a end-to-end process. So that's how I see that those two things can be complement to each other.
Very cool. Hi, Chen, would you like to comment on that? Any opportunities about these technologies working together? How Seno might complement zkPyTorch, in practice, real world impact.
Yeah, I sound like that Zhengfei already talk about the potential, the way the Seno and zkPyTorch can integrate and then complement each other. Where I treat so first of all, both project is building backend inside the GKR, which means it's definitely easier to integrate together. Because you basically you're talking the same language, so that it's much easier for you to communicate with each other. Whereas other zkVM, it's definitely harder to do that. And then I do see I think the analogy is that the Seno is more so it's a CPU, where zkPyTorch more is a GPU, which can really accelerate speed up for those machine learning models, which similar to CPU and GPU. You do for your machine learning model to work, you have the CPU to do a lot of the basic integration and other stuff, and then for those matrix modification, then you can hand over to the GPU to have achieve really speed up for you. I do see the same the synergy between the Seno and the zkPyTorch.
Awesome.
I love this CPU GPU analogy. I think it's really great.
Yeah, I just wrote that down. I was like, that's brilliant. Yeah. I really like that. That was great, guys. All right, I know we're at half an hour. We're still going good before we can jump into a few community questions. So I might jump ahead a little bit. I've got a lot of questions, and I have based a lot of this conversation around questions from the community as well, so that we can give the people what they've been asking for, and I can see how many comments are coming through. People are really liking this episode, guys. We got a lot of people live here as well. So maybe would you like to expand on that from a zkPyTorch perspective, Zhenfei?
Sorry, I missed the question. What was the exact question?
Based on the use cases, did you want to expand on that, or are you happy with the response?
Sorry. Probably maybe let's go a little bit more specific on the question. So
that's all right. I think we dived into the real world use cases and the synergy there. I'm super happy with that, and I know that the community as well. So maybe before you know what? I think that we should look at future vision here. So looking ahead, guys, like where do you see these technologies in the next, say, 3 to 5 years? You know, Haichen, what's your vision for Sino and you know zero knowledge, you know, virtual machines more broadly?
Yeah, I think like for Sino is that so currently I see like zk technology is more inside like a very niche topic. Although like I think in the blockchain is no longer like people are already familiar with this as a verified computation using zk. But I do see like in the 3 to 5 years with all of the zkVM and all of the optimization we've been putting together, so that we can lower the overhead further and further, like the from like original maybe like 7 to 8 like order of magnitude overhead, now like to 5 to 6. And I do see like if we can push in like little further to lower like overhead like compared to your regular computation like then I do see like it can potentially have more like a mainstream adoptions inside or like beyond the blockchain. And also the zkVM, the beauty of zkVMs are like the people no longer need to write their own zk circuits for the applications. They can use their regular compiler and then execute it, like and then compile and execute it, and then the zkVM can help you to prove that your computation is done correctly and to make it verifiable very easily by the verifier. So I do see like if it can go like in the 3 to 5 years, I can go beyond like the blockchain and having other applications like on the cloud or like on the mobile phones. They can do like more verifiable computations, use cases and adoptions. Yeah, and then also like I think there's like could be like potential sometime like the people or like there some hardware accelerations can pushing like the performance breakthrough, so to make it more closer to real-time computations. I think initially I do see like in 3 to 5 years, it is possible like the zkVM performance is now like the up to another stage, so that it can really like embed it inside the Ethereum layer one. So within the single block slot or like the 1 to 2 blocks slot time, like you can then using the zkVM to verify all of the transaction processed correctly, so that now the validators, they no longer need to re-execute all those transactions. They just need to verify a small proof, which is very lightweight. So they can save a lot of energy, and then it can make potential like a lot of like scaling factors for the Ethereum and other blockchains. And then like we do see like the Steno, we hope like it can achieve this visions by utilizing the GKR and to pushing the boundary of the zkVM performance.
Awesome. Thank you for your perspective there. And knowing you guys and the way that you guys work, when I asked 3 to 5 years, I know that you know, we're probably going to see this in a year. You know, you tend to be quite conservative and then do these amazing things. So thanks for the perspective. You know, Zhenpei, you know, I love asking you this question, man. Like what 3 to 5 years, you know, what's your outlook?
Right.
Maybe like more specifically ZK PyTorch and verifiable AI.
Right. I guess I mean I've been answering these questions quite a few times. You always use
Yeah.
this HTTPS analogy, so I'm going to save that. And if you want to know what it is, then probably look at previous shows from me. So this time I'm going to give a different answer, like maybe just and a cue to the zkVM talk, right? If 3 to 5 years, if the Ethereum Foundation's beam chain roadmap execute well, then we will see the zkVM getting integrated into the consensus, and everything is there. And in that future, what we can safely assume is like the proving speed will be so drastically improved, because now you can already prove the Ethereum transactions within a block time, and that means you must have a great advance in your proof systems, in your protocols, in everything, right? And by then, we would safely assume that similar scale, similar order improvement happens for the zk PyTorch, happens for the zk machine learning, happens to us as well. So what we want to really see is real-time proving. Similar to the real-time proving for the blockchain, we have a real-time proving for the inference. So the moment that you generate the inference, you get a proof that the inference is correct. And hopefully by then we can also see these proofs getting deployed deployed on chain. So you can see. I mean, some of the proofs have already been deployed on chain, but it takes a little bit time. So, I guess by then we will see much more applications in Web3 because we can prove in real time and we can verify the proof on chain instantly. So we will see like decentralized identities or like verifiable trading bots. All these things that has some limitation to deploy due to the computation nowadays will be very easy to use in 3 to 5 years.
Brilliant.
So,
Thank you guys. I'm looking forward to it. I'm looking forward to a verifiable future. And yeah, love it. Thank you for making that happen, gents. So very, very cool. One quick question before we might just get into, I know that you guys will, you know, you've got very, very busy days ahead, but a quick question for both of you. I know we've got a lot of developers in our community and watching right now. So what would you say to developers who, you know, are interested in getting started with these technologies today? You know, and what's maybe Haichen to start, like what's some advice you could give to somebody who's looking to explore Sino or zkVMs in general?
Yeah, so if like for developers who are interested in contributing Sino, so Sino is fully like developing the open source. You can go to github.com like scroll tag /Sino, then you can find the project. We have like issues, so and also all of the PRs. If you're like interested, you can take a look at that. And also you can check out the Sino paper to see like the original design, like all of things, and also you can see the latest development on the Sino. So I think like that's how like if you're interested, we're definitely welcome for the open source contributions.
Brilliant, brilliant. And Zhenfei, what about you, man? You know, what about I know you've commented on this before, but you know, I'm sure we've got some new people watching. What about AI developers interested in using zk PyTorch?
Yeah, I would say like get your hands dirty and get started with some small models and try to get familiar with the whole workflow and then generate proof. Trust me, like the first time that you generate proof, you will be very excited. And I guess the key challenge is try to just get started and get to understand the pipeline. And it's a little bit different from from how the AI community works, but once you get familiar with it, I think it should be seamlessly integrated. Sorry, our goal is to have the zk PyTorch seamlessly integrated into the PyTorch. So I mean, for the AI developers, if you just run through the process for one time, then everything should be quite trivial for you. So yeah,
Awesome.
Just play with it and let us know your feedback and let us know how we can improve your experience.
There you go, guys. From Zhenfei, get in there, get your hands dirty, and start experimenting. I love it. I love it. Okay, let's move on to some community questions. We have had over 1,000 questions again for this show, guys. And I was just reading through these questions. I was like learning a lot because I was just like, hold on, really, really great from the community and some really, really deep questions. But one that jumped out at me here is really great, I think. So let me just scroll through these here. Okay. Are there any plans to make these technologies available as cloud services, or will they be primarily for on-premises deployment? So maybe Haichen, what's Scroll's approach here?
We definitely want to make it available for other if you want to deploy your own sensor or make it possible to deploy it. Yeah.
Awesome.
Yeah, I think
awesome.
Yeah.
And Zhenfei, Polyhedra's approach to deployment.
Yeah, we will have cloud service for this. We are actually building a cloud service for our prover. So with that, you probably can not only run zk PyTorch, but also run a few other provers and maybe also including Sino. Let's see. Yeah.
Awesome. Moving through, let's have a look here. Maybe how here's a good one. How do these systems handle proprietary models? Can I prove properties about my AI without revealing its weights or architecture?
I guess that's a question for me. Yeah, so well, there is, sorry, let me try to reorganize a little bit. So what we are working on is so-called zero knowledge truths, right? So it's zero knowledge means that you don't learn anything. That means like if you are working on a private model, then the model is not actually leaked. So so that's guaranteed by the protocol itself. Although in practice we may have some side channels, we will need to really look at it from case by case. But in general, you should be able to you should be able to protect all your secret, including say your the weights, the parameters, or everything, and for your model.
Brilliant, brilliant. One just to wrap up the community questions here, because we are running out of time. I'd love to know the answer to this one, which is, what's the biggest misconception about verifiable computation that you'd like to correct? I mean, I know that there's a lot of misconception in the market about speed, for example. But what are your guys' angles on that? Maybe you can start, Haichen.
I think like so I can say like some like previously I know a big misconception, but it's not like about verifiable computation. It's about like actually zk. So when like the people originally heard about zk rollup, because thinking like it's private chain, it's a privacy rollup, because like they have the zk zero knowledge, so that people doesn't know any transaction. But actually, the zk rollup is probably like a better name. Maybe it's a validity rollup, where like you use like the verifiable computation from the zk side. It's like it doesn't hide anything from like all of the transactions. So the transaction still process information that publicly, but we're just using like make all of the transaction processing verifiable on the layer one, and then like you basically compress like tons of transactions together into a single very succinct proof that can be easily and cheaply verified on the Ethereum.
Brilliant, love it. There you go, guys. And Zhenfei, what misconception would you address, man?
Right. Let's see. I would say like also the title, the zk part, right? So usually when I heard about zk, I really have no idea what it is, because it's zero knowledge. But the point is, I guess the point is not intended, but the point is like you really don't need to have any knowledge to be able to use zk PyTorch or any zk tools like the zkVMs. The idea of all these things, maybe we need a better marketing for this, or better slogan for this. The point of all this, all the tools that we're developing and Scroll is developing, is try to make those tools painless to use. Like you should be able to use everything without knowing what's inside it, what's underneath it. Right? You shouldn't really need to learn assembly to be able to write C code. So we are writing the assembly, and we are providing the developers with C code, and that's the idea. We are not asking developers to write assemblies with us. So that's the biggest clarification that I want to make.
Awesome. Thanks so much, guys. This has been an incredibly insightful discussion. I think I'm going to have to come back and watch this episode a few times to be able to distill it all. But I know that, yeah, again, guys, we've got well over 1,000 people viewing live right now. I know that there's a lot. I've been monitoring the comments here that are coming through. There's a lot of love for you guys, a lot of appreciation. So thank you so much for sharing your insights and all of your deep knowledge, and even breaking it down for a layman like me. It's been really, really great, and I appreciated you guys taking the time. Any last thoughts? Maybe Haichen, you can share, where can people follow, obviously your X and your website, and where can developers get in touch with you, man?
Yeah, just follow. I think I go. You can follow the Scroll zkP on the Twitter, on the X, like that. So you can get the latest news and the latest like development progress on the of Sino and other related like the technology updates and also ecosystem updates from Scroll. And then if you're like a developer, you really want to know like what's like going on in behind it, you can feel free to check out our GitHub. And so you can find all of the things, and you can potentially collaborate with us and then become like a part of us, like to making the zk more like accessible to everyone sooner.
Awesome. Make zk accessible. Let's bring on the verifiable future, guys. And Zhenfei, any last thoughts from you, man?
I guess similar things. Come and build with us. This is the invitation. Yeah.
Awesome. Open invitation, guys. So yeah, get involved. Let's build that verifiable future. We need bright minds like these gents, and we need bright minds like yours to help us to make it happen. Awesome. Thank you so much. I really enjoyed this episode, guys. It's been an absolute pleasure. And thank you for taking the time to with me and with the audience. We really appreciate it. And I'm sure we'll see you guys again on the show. But yeah, until next time, thank you so much and have a great day, guys.
Thank you.
Thank you for having us.
Thanks, guys. See you next time.